Hello, I am recording this video to give you guys some extra review on doing these hypothesis testing. I understand this process is pretty detailed, and if you do not get it on the first go, that is very understandable, but stick with it. And if you want another explanation of, I'm going to do one problem from Lab 9A and one problem from Lab 9B to allow you to check your work, follow this process, and it's identical the process on other problems. You're just repeating it with different numbers. So hopefully this helps give you familiarity if you need it. Okay, so this first problem, this is again lab 9A walkthrough problem 10. It looks like we got this situation where people are guessing if Facebook recommends their data accurately. So 67 or 0.67% say it's accurate. So we're going to call that p hat, 67%. And this was a total sample of, it looks like 850 people. So we're going to say, the question is, do they categorize accurately? The null would be, no, there's nothing going on. Facebook is random. In which case, we would think about 50% of the time they'd get it accurate. So that's our P. And the alternate says, no, Facebook is accurate. So we're going to expect to find a P that's greater than 0.5. So to check these conditions, I'm going to use these two values here. Success and failures. I'm going to call this P just so I can have less typing. N times P is the successes, N times 1 minus P is the failures. And so we can check that to say, hey, look, there's at least 10 successes and failures. This means we have a big enough sample. Proceed. And we want to assume they used random sampling. So we could say random sampling used. We should say if random sampling was used, which I don't think it says in the problem. No. But we're going to assume they know experimental design. Then we can assume independence. We just don't want there to be links between our data so that we can use the central limit theorem. So to find this, we first need to find the 95% confidence interval, which is, the formula for this is P plus 1.96 times SE and P minus 1.96 times SE. And so we already found out that P was 67%. That was given by the problem. That's data from the problem. And N was 850. So we'll say P times 1 minus P divided by 8 divided by N. So I'm going to put that there just to see that my number makes sense. Yeah, that's a reasonable number. And so here's our confidence interval, 63 to 70%. And so based on this, null is outside this interval. That 0.5 value is outside. So we reject the null. This means rejecting the null is good. This means we have evidence of the alternative, which to interpret this in context, we should say what the alternative is. Facebook is accurate. So we always should interpret this in context. These aren't just numbers. They tell us something. So now we can do the same step, the same analysis using p-values. And generally, p-values are a little more complicated, but they're preferred because they tell us our answer with some degree of accuracy. You know, we can know based off of probability how accurate our conclusions are. So to recalculate the SE, I'm going to copy paste all this. To recalculate the SE, when we're doing hypothesis testing, really we're assuming the null is true. So we should say that's what P is, 0.5. And so when we recalculate the SE, we get something that's slightly different. And based off this SE, I'm going to draw a picture here for you. Please, please, please draw the picture. Otherwise, you might just be guessing and getting something that's kind of off. So what's the picture here? The null hypothesis tells us that we're assuming 50% of people are getting their categorization accurately. And we got an SE that was 0.017. So that's what we know. Now I'll draw the next part in a different color. Our data, we got 67% was what we observed from our sample. That's our p hat. So now we want to say p-value is a chance observing our data or something more extreme. So it's inaccurate saying it's to the right. So now we can find that probability. Since it's right, it's 1 minus. And then we say what we observed. This is our point, and then the mean, standard deviation, which is our standard error. And if I just calculate it here, I can be assured that I'm putting in the right answer. If not, I can copy paste that in there. The answer I'm getting. Now, if we get 0, don't be alarmed. That means it's a very low probability. So very small p, close to 0, means we reject the null. That's kind of my note. So this means we have evidence for the alternative. At least more accurately than random chance. So that's an example of how to do one proportion testing, Lab 9A. And so now I'm going to go on and make sure you understand this, have these steps down, check your work, and go on to Lab 9B, and I'm going to do the CPR problem. This is a different problem because we have two proportions, and so the procedure changes a little bit. So to do this, I'm going to say what N1, P1, N2, P2. We got two groups that we're sampling from. So if N1 is a control group, we had 50 patients there, and 11 of them survived. 40 patients are in the treatment group, 14 survived. We want to know, is there a difference between these proportions? Oh, and these proportions should really be divided by 50, divided by 40. I just gave you numbers, they're not proportions. So N, P1 and P2, I kind of want to see what those are to see if there's a difference. Okay, these are the two proportions. P1 is the proportion of survival in the control group. P2 is the proportion of survival in the treatment group. Okay, there's a difference there. You can see at P1 minus P2, there's a difference of about 13%. That's pretty significant. Well, we can't say it's significant because maybe this is happening due to random chance. So thus we need our hypothesis test. So the hypothesis says, no, there's nothing going on. There's no difference. So that'd be the same thing as saying P1 minus P2 equals 0. No difference, 0 difference. Alternate says there is a difference. P1 minus P2 is not 0. So to check this, we have to do our assumptions. N1 times P1, N1 times 1 minus P1. Remember, 1 minus P1 is the probability of failure for that group. So this gives us both the numbers for success and failure. And N2. Those are the successes and failures in the first group. And we narrowly have big enough samples. So samples are big enough. Again, we'll assume independence. So now to create our confidence interval, the formula for a confidence interval is P1 minus P2. That's the thing we're trying to estimate, the difference, plus 1.96 times SE, and the same thing minus. So we got to find our SE. What's the formula for SE? The difference of proportions, we have to do P1 times 1 minus P1 over N. That is actually the variance for the first group. We're going to add it to the variance for the second group and then take the square root. Check that. Make sure that number makes sense. I did it correctly. That gives us our confidence interval, which says, ooh, there's a difference. This says the control group is between 8.7% and 17.2% less likely to survive. Okay, that's significant. And so based off this, that null value of 0, it's not in there. Evidence, sorry, not the control group. Oh yeah, evidence the treatment increases survival. That's pretty significant. This is not just random here. We have evidence to reject the null, which says there is no difference. There is a difference. Okay, so now this test might be more intuitive to understand, but generally we prefer the p-value because we can use some kind of certainty, some kind of probability to calculate a result. So to do this, we got to find out the pool proportion, N1 times P1 plus N2 times P2 divided by N1 plus N2. And you'll notice this is the total number of successes in the first group, the total number of successes in the second group, divided by the total. That's a proportion of everyone there. And now I'm going to find out my new standard error. I'm just going to check these numbers so they make sure they make sense. I always like to see them. Okay, that's a proportion. It's a number between 0 and 1. Somewhere between are the two values. So now instead of looking at, ooh, but I made a mistake here. I should say N1 and N2. Oh my goodness, that's going to change my answer. So notice I had a previously, from the previous lab, I was using N, and I found out that I was using the wrong numbers there. So that changes my answer slightly. Let's fix that. Between 5%, 5.7% less likely, and sorry, 5.7% more likely, and 31.7 less likely to survive. Okay, this changes our conclusion. I made an incorrect decision previously. Now the null is in this. Notice 0 is between the positive and the negative number. So we do not have evidence of difference. We don't have evidence to reject the null. Null. So thus, we do not have evidence of a difference. Okay, that's significant. And this is good. We can check it with what we're finding here. So now we got our better pool proportion that I'm doing correctly. I'll check those formulas. Okay. We have a distribution again. Always draw that picture. Here's the null hypothesis says 0 difference. SE is 0.095. This number is significant. This tells us how far of our spread is. And so when you observe something like, what was the difference we observed? Difference we observed up here was 13%. Oh, gotta get a better pen. We observed negative 0.13. That was the value we observed as a difference. What's the probability of getting something less than that? That's this right here. That's a lower tail. So it's 1. It's just p norm. Of the difference we found, the mean was 0, and the standard deviation is the SE. What do we get? We get a decently big value. This value is more than 0.5. But if we want to compare with alpha equals 0.1, there is a difference. So if we're going to compare 5.6 is greater than 0.1, we have evidence difference, but it's not strong evidence since this is a high high significance. So we have evidence of a difference, but it's not strong. So if I want to go back to my confidence interval, again, I made a mistake. I used the 95%. So if we want to use the 90%, I forget what that number is. Q norm 0.9, 0.1 divided by 2, 1.64. That's our confidence interval. So this is a case where our confidence interval shows the null. We have to reject it. But I'll change these numbers. 2.6, 28.2, 6%. We do not have strong evidence here. But consider, we didn't really use the pooled proportion here. We didn't fully use the power of the assumption of the null. The null says there's no difference. So when we use that pooled proportion, we're assuming this is true, and we're able to build a better case to say that there's a difference. And our p-value here, again, it's not super low, but it is low enough that with 10% confidence, we can say we have evidence of a difference. And this is what statistics gives you. It gives you an ability to make a decision knowing with some kind of probability what the chance is of making an error. So in this case, we have a 10% chance of making a type 1 error. That is rejecting a null that's not true. So now we can proceed. We can give this to doctors to know, hey, there's a 10% chance that this will make a difference. Well, I can't quite say that. We have evidence with 10% confidence that this will make a difference. So that is the process for doing p-values. And my encouragement to you is to practice again and again and again. You'll get better and better at piecing all these things together, and each case might be a little different, but you can pinpoint the common steps and get good at those, so that maybe you make one small step. Well, I'll tell you this, if you want help setting up the null hypothesis, if you have questions on that, I'll always, in this class, help you, because that's a little tricky. But the rest of it, I think you are set up to do. I'm confident you guys can continue on that. Okay, I hope this helps. Just extra resource, extra way to check if you need it. And that, now it's on you guys to practice.